Good morning, all of you. So, it's the beginning of a new week, and we are ready to start a new subject or a new topic in our course of physics. All right. So, up to now, if you remember, we have been talking about quantum mechanics. We have also talked in very brief about classical mechanics as such. But this time, I'm going to introduce to you a third subheading of mechanics as such, which is called the statistical mechanics. All right. So what we are going to learn or we are going to talk about today is called statistical mechanics. Now, what comes to your mind when I say this term statistical mechanics? Are you not thinking that does it have anything to do with statistics? The answer is yes. It does have a very big contribution from statistics. By the way, what do we do in physics? Be it classical mechanics or quantum mechanics. Generally, what are we interested in? We are interested to know how a system evolves with time. Remember, when we solve the equation of motion in classical mechanics in terms of Newtonian mechanics or the Lagrangian formulation as such, when we are talking in terms of the classical mechanics, we solve an equation of motion so that we can know how the position of a particle changes with time, isn't it? So when we know that how the position is changing with time, what essentially are we finding it out? We are actually talking about the time progression of the system, as in how the system is varying with time. Similarly, when we talk about quantum mechanics, instead of the particle nature of our system, we delve into the wave nature. However, in order to talk about the wave nature, finally again what we do, we find the time part, we find the position part of the wave function, and ultimately what are we trying to do? Again, we are trying to talk about the position and in terms of how in time it is going to vary, isn't it? But think of a situation when we are solving the equation of motion of one system, or we are talking about the Schrodinger equation of one particle. Essentially, what are we concentrating on? We are concentrating on a single system or a single particle, isn't it? But now, if I want to know what is happening to, say, the atoms of water in 1 liter, that is, what is happening to all the atoms which are present in a liter of water, only a liter of water, which we always carry with ourselves in a small little bottle, right? Now, just think, how many atoms of water do I have in that particular bottle in 1 liter? It will be in terms of the Avogadro number, which is 10 to the power 23. Right. So even when I am talking about a small system, a small real life system of 1 liter of water, I am actually having as many particles, which is comparable to 10 to the power 23. So if I now want to formulate equation of motion of each of these particles, and if I want to solve all of them, think what will be my condition? Isn't it? So when the number of particles in a system is very high, which is actually the case in our real life, it is very difficult for us to actually concentrate on a single particle's motion, a single particle's equation of motion and solve it and delve upon all those essentially individually. I hope all of you will agree with me if I say so, isn't it? Right? Can I have some feedback? Please try to think with me that when we are trying to think about one particle's equation of motion, I will write down the equation of motion, I will put in all the conditions and I will solve it. But when I have to do it for 10 to the power 23 of such number, then will it be very easy for us? No, not at all. Then what happens? Instead of actually concentrating on a single particle and how it is behaving, we rather change our perspective. We no longer want to know the individual particle's motion or the individual particle's equation of motion and solve it. Rather, we then try to approach it like the entire system. We consider it as a system of identical particles, as in all the, say, water molecules, as in the example I was telling you, and then we try to look at it from the angle of statistics. What is statistics? What essentially does statistics? In statistics, what do we do? Remember, we take the data in the beginning from a large number of samples And then finally, we come up with a formula and assume that all of these samples that we had created, these individual systems will be following that particular formula. Isn't it? So the same concept is also used in statistical mechanics. So when the number of particles in the system becomes very large, we generally tend to look at it from the statistical point of view. We try to look at it from the probabilistic point of view. Because remember, in statistics also, most of the results are probabilistic. I will come into more detail about it very soon. So when I say statistical mechanics, please understand the fact that in this case, we are not going to talk about a single particle or its equation of motion or its behavior. Rather, we are going to consider a system with large number of n, and then we are going to find out some formula, as in we are going to find out some particular characteristic of the entire system, and we will assume that all of these will be following the same rule. Okay. Now let me give you a very easy example, or rather very trivial example. Say when you are at your home, your parents are very interested in how much you got in physics, how much you got in mathematics, how much you got in English, right? But now the same student, when he comes to a college, in that college there are large number of students. Somebody is going into electrical stream, somebody is going to CS, somebody is going to IT, and so on. So when the college looks into the performance of these students, the college essentially is not interested to know how an individual student is performing in maths or physics or English. Rather, what we do, in general, the college will be considering that, okay, these are all CS students, so there has to be some similar characteristics of all the CS students. And what would that be? Say they are all good in coding. And suppose these are set of electrical engineering students, they will all be good in, say, electrical theories, right? So instead of individually peeking into your result books, there is a certain a view from outside. As if we are looking it from outside, we are formulating a kind of rule that, okay, CS students will be good in coding, EC students will be good in, say, microprocessors, and so on. So in the same manner, think of this example and let us translate this very example to physics. So instead of continuously thinking about one individual particle's motion, one individual particle's energy, one individual particle's momentum, we are now going to look at it as only a part of the entire system, and we will see that are there these kind of categorized rules which these particles will follow. So this is what is essentially statistical mechanics. Okay. Yes, Arjun, you are exactly right. There is a very big role of data collection, calculation, and understanding the data. And once that thing is done, there is a particular rule written that, okay, for this kind of a system, this will be the general behavior. And that has already been done by our scientists from long ago. And today we are going to just start the beginning of statistical mechanics. We will just learn how to step into this vast system. Okay. Now, as you can see, today we will learn about, today's class is going to be very small. We are actually going to learn about 2 points, which is one of them, which is called the, and second what we will learn is called the microstate. Okay, so if I am able to explain these two, today's class will be good. Now, before I directly jump into macrostate and microstate, let me give you a very little introduction. And what is that? In statistical mechanics, essentially, when we are considering about a system, there are a few assumptions that we will always consider. Okay, so as if those things are always going to be true. And what is that? That in a system, in a particular system, whenever I have a system, all the particles in this system will be considered as identical. Okay, all the particles constituting the system will be considered as identical. And by identical, what do I mean? By identical, I mean, say, suppose your class is under study. So there are 47, number of particles is 47. And essentially, what is the identical characteristic which all of you have? That you are a second semester student of electrical engineering. So in this perspective, all of you are identical to me, whether you are a girl or a boy, or you are coming from this background or that background, is not the matter. Rather, what I am going to consider is that each one of you is the student of electrical engineering in second semester. In the same manner, in our statistical mechanics, when we talk about the system as such, please understand that we consider that all these particles which constitute the system are identical in nature. Okay? Now, once we have talked about this identical part, we will also assume that the system is in thermal equilibrium. Please try to remember the term. We will consider this to be in thermal equilibrium. Thermal, if I ask you what is related to thermal, which means temperature. So, when we are considering or when we are talking about a statistical system, we will consider not only that their particles are identical in nature, that the entire system is in thermal equilibrium, which means at this moment when I am doing the calculation, its temperature is not changing. So see, when can I assure that the temperature is not changing? When it is not going to interact with the environment, isn't it? So we consider that this system will be an isolated one. The term isolation is once again coming in. We all are isolated now from each other. And this system that we are going to consider under the statistical system will also be considered to be isolated. Isolated as in which is not interacting with its environment, and hence its energy is remaining constant and its temperature is also remaining constant. So is this clear? So let me summarize once again what I have said, that a statistical system consists of identical particles. That system is considered to be at thermal equilibrium with its environment, and its energy also does not change, is also essentially not changing. And particularly when its temperature is same, when its energy is not changing, another quantity will not be changing, and that is the number of particles. The number of particles in the system also will remain constant. This number of particles is actually the one which is constituting this system. Okay, so we have said a lot of things. Please remember all these things little carefully. All right, so then when we have understood this part, now we are ready to go and learn about micro and macro state. Fine. So the system that we are now considering has n number of particles. The system has a fixed energy E, and it is not interacting, it is not exchanging its energy with the outside, which means its energy is not reducing or its energy is not increasing. Fine. And in doing so, the temperature of the system is also not changing. Fine. So with these things in our mind, let us go and talk about this macro state. So essentially the most important terms which we are going to always follow when we talk about the macro state is the number of particles of the system and also the energy of this system. So these two are our best friends from now onwards. Whenever you are dealing with a macro state, the two tools that is most important is N, which is the number of particles, and E, which is the total energy of the particle. Fine. Now, when will I call the state of a system as macro state? See, macro state, when you are going into your books or when you search in the internet, you will see that there are basic definitions of macro state given. I am not going to tell you any definition as such. But what I want you to understand is that when we talk about the macro state of a system, it is as if we are looking at the system from outside. I do not know what is happening inside. I only know that the total number of particles is N and the total energy of the system is E. Okay, so this very concept, so this very information that there is a system with N number of particles and a fixed energy E whose temperature is not changing, also its volume is not changing, is the macro state of the system. So this is as if I'm looking at the system from outside, from a macro level. We all have discussed about this macro and micro concept already. So as if when I'm looking at the system from outside, I'm looking at it in the macro perspective. So all I know in terms of the macro state is what is its total energy, and this total energy is occupied or is being had by these n number of particles. Fine. Now, from here, when I want to know or when I want to go deeper into the system, when I want to know that how this total energy has been distributed to these n number of particles, I will have to go deep. Are you following me? I knew that there are n number of particles, all of them together are having an energy E. That's all. That was my macro state. But now I want to know that these n number of particles individually, how much are they having? So that when I add up all together, this total energy will be received. So in this case, what am I doing? I'm going deeper and I'm trying to know about the individual states. At that time, as if I'm peeking into the inside, and then I am coming into the micro state. Right? Then I'm coming into the micro state. So this is overall the explanation of macro and micro state. But you all will now understand it better when I tell you with the help of an example and we actually solve this problem. Okay, so now let us try to see an example where I will show you how to write a macro state and micro state. It will be very, very easy for you all then. Fine. So for simplicity, let me begin with a very, very easy example. And what is that? Let us have a system, say, with n is equal to 2 particles. Starting from a very, very easy example, I have taken a system of identical particles with n is equal to 2. Fine. And the other thing which I know is its total energy is, say, some 4 epsilon, where epsilon is the unit of energy. So, see, when I know this, that there are n number of particles is 2 and the total energy is 4, this is a macro state as if I'm looking it from outside. So, how will I write this in terms of the language of statistical mechanics? Now, let us delve into it. Let us see. So, what we will do now in statistical mechanics also, we believe, or rather it has been formulated on the belief that energy is quantized, which means energy will be allowed to only have discrete values. So, when I am going to define this system, I will also have to define one more condition. And what is that? N is equal to 2, total energy is equal to 4E, and this 4E may be had only in terms of 3, say, systems, 3 energy levels with 1 epsilon or 2 epsilon or 3 epsilon, which means these particles that we are considering cannot have any arbitrary value. It can either have 1E energy, or it can have 2E energy, or it can have 3E energy. With this condition imposed, in how many ways can I write this so that these two particles will have total energy 4? Please try to understand. The question is n is equal to 2, which means there are 2 particles and total energy has to be 4E. However, there is a condition that either the energy has to be 1E, 2E or 3E. Let me give you the first answer myself. Then I will ask you the second one. I hope all of you we will agree if I say put one particle in first state and another particle in the 3E state. Is it not? Then my total energy is 1 plus 3, 4 and there are 2 particles. Am I right? Now Shrestha has asked that should it have energy less than 4E? No. It means that the total energy of the system is 4E. And this 4E will be occupied by these 2. So, one of the situations arises that one of them is at E and the other is at 3E. Correct? Very nice. So then now, how will I express this information in macro state or microstate? Now see, in general, the notation that we use is a bracket, and we begin with the lowest energy level first. We will write about the number of particles in the first level. So I will write 1 because there is one particle in the first energy level. There are no particles in the second energy level. So I will write it as 0, and there is one more particle at the 3e level. So I will write this as 101 within brackets. And this denotation is the first macro state. So this denotation will be called the macro state. Now you may ask me, why macro state? It is macro state because, see, I know that there are two particles, and I have seen that one of them is having an energy E and the other is having an energy 3E. But remember, I don't know that among these two, which one is here and which one is there. I am only looking it from the outside. The total energy is 4 and there are two particles. So in this manner, when I write 101, this denotes the first macro state of the system. Is this clear? Please let me have some feedback. Yes. So we are having a 101 macro state. Now my question is, now all of you think, is there a possibility of a second macro state where still I will have number of particles 2 and total energy 4? Is there another such possibility? I would like to have some answer. Yes, tell me. What will be the other option? What will be the other option? See, Sandeep has written 110. 110. So if I put 1 over here and the other over here and 0, then what is the total energy coming out to be? It is only coming out to be 1 plus 2, 3. So my total energy is not coming out to be 4E. Yes, very good. Shubhronil, Vanshika, Sandeep now is right. So you all have exactly come up. Rupam has also come up with the right answer, that it is not anything else but as if both of them will be in the second level, and we will write this macro state as 0 to 0. Very good. Very good, all of you. So see, when I write this or I write this, the only information that I have is there are two particles and the total energy is 4E. I do not know that which particle is sitting having an energy of 1E or 3E or 2E, right? So like this, when we denote, we are denoting the macro state, right? Now let us go back to the first example. Let us go back to the first example and try to understand from this macro information, how will we find out the micro state, right? As I was telling you, what is a micro state? The total number of ways in which total energy E can be distributed into n number of particles is the so-called definition of microstate. But when I have to write like this, among these two particles, all of them are identical. But suppose I name one of them as particle A and I call the other particle as particle B. Did you understand? All of you are second semester electrical students. But one of you is Arjun, the other is Shrestha, the other is Naina. Like this, I can always distinguish you all. So in this manner, I am distinguishing these two particles and I am calling one of them as A and I am calling the other as B. So in this scenario, either A can be here and B can be here. I hope you will agree with me. And there is another possibility that B is having an energy of epsilon and A is having an energy of 3 epsilon. So in this case, belonging to this 101 macro state, how many micro states do I have? I have 2 two microstates. And what is that? One is A0B and the other is B0. Do you all follow me? Now that I have delved deeper into the system, I know that B has an energy of 1, A has an energy of 3. Or in the other case, A has an energy of 1 and B has an energy of 3. So when I am looking from outside and I know total number of particles is 2, total energy is 4, this is the macrostate. Whereas when I have gone deeper and I have found out who has how much of energy, I am talking about the microstate. So did you all follow about how to write a macro and a micro? I hope this was easy. Yes, Ankur, it is 0 to 0. We will come to this next one now. So if we have understood how we have talked about the macrostate for 101 and then how we have written down its microstate, now let us talk about the 0 to 0. Fine. So now what is the particular example that we are talking? We now know that both of them are at the second energy level. But this is here, I have to tell you one thing, that when both of the particles are occupying the same energy level, whether I write AB or I write BA, this is not going to be making any difference. So for the system where both of these particles are occupying the same energy, when I interchange their positions in AB and BA, this will be the same. So corresponding to this macro state of 0 to 0, I will have only one microstate. And how will I write that? 0 ABC. One could also write 0 BA0 because that also will be having the same meaning. So did you follow? Now Rupam is asking 011. Why not 011? See, when I put 011, which means there is no particle in the first level, one over here and one over here. Then when I add up the total energy, what is my total energy coming out to be? 2 plus 3, 5. But we have already said that the total energy is 4. Right, Rupa? So now can you understand why we cannot have the 011? Yes, correct. Shovik, you are right that you have said that it is either 0AB0 or I could also write 0BA0. These two are same. Okay. So this is how this is the nomenclature. This is how the writing is done for a macrostate and a microstate. Okay, now there are only 12 minutes left for the finishing of the class. I will not be going beyond 12:30 today. So I will just give you another example. We will do one more example and our class will be done. Okay, so let us do one problem. Yeah, I always tend to, why don't you people have your names in your IDs? You all will be putting up names like this and I won't be able to recognize. I'm so sorry. All right. So now the last example today, and I'll be bidding you bye. Then let us come back to our new example. What example can I give you? Okay, let us have now little bit of higher level. That is n is equal to 3. I'm giving you a system of n is equal to 3. Total energy is equal to 6. Total energy is equal to 6E, or rather I should be writing it as a 6 epsilon, and the allowed values are epsilon, 2 epsilon, 3 epsilon, 4 epsilon. Let me explain this to you once again, that now we are excuse me, now we are talking about a system which has n is equal to 3, total energy 6 of unit epsilon, and the allowed values of energy that these particles individually may acquire is either epsilon or twice epsilon, thrice or 4 times epsilon. In this scenario, the question is to write down the macrostate and also the microstates. Come on. So what do I have? What can I do? So Rupam is telling me that I may have 1, 2, 3, which means 1, 2, 3 means there are only 3 particles. Then how can I write 1, 2, 3? I can have 1, 1, 1. I can have 1, 1 and 1. So see, since we are having 4 levels, remember we cannot leave this like that. When I'm writing this, I will be writing it as 1, 1, 1, 0. Because the allowed fourth level does not have any particle in it, so it has a 0 occupancy. See, these numbers that we are writing essentially over here are the occupancy, isn't it? So if there are 2 particles, I will write 2. If there are 3 particles, I will write 3. So in the first level, I have kept 1 particle, the other in twice E, and the other is 3E. When I add them up together, correct, we are getting 6E. All the 3 particles, n is equal to 3. So this is an allowed macrostate. Very good. This is 1, 1, 1, 0. Correct? Now, before we go into the other macrostates, first I would like to know what are the possible microstates of this macrostate. Can you tell me? Now, say there are 3 particles. One of them is called A, the other is called B, and the last one is called C. So, how many possibility? What are the number of possible microstates for the same macrostate 1110? If I want to write now, I can write it as A, B, C, 0. Please bear with me. Please try to understand. I can write A, B, C, 0. Or I could write A, C, B, 0. This is also allowed. I could have B, A, C, 0. I could have 0. Finally, I could bring in C in the first. Are you all able to see all that I'm writing? So when I have the macrostate 1110, please see that we have come with 6 microstates possible. So only for one macrostate, the total number of microstates in this case is 6. Isn't it so interesting that only when I have increased the number of particles from 2 to 3, now the number of microstates is increasing in a very large order, isn't it? So for 1110 macrostate, there are 6 microstates available. Correct? Yes. How many? Yes, Rishabh has said the right thing. We have 6 microstates. Many of you, no, Shubhronil, it is not like that. So what has 3 factorial? 3 factorial, yes, it would be 6. But let us see if this thing is possible for everything. Because not always this formula will be 3 factorial. In this case, it is somehow getting equated to 3 factorial. Fine. Now, when we have talked about the first macrostate, let us come to the second macrostate. What is the other macrostate possible? So, please, let us just write it down. That for 1110 of macrostate, we had 6 microstates. Let us remember this. Now again, we are back to filling our energy levels. Epsilon, twice epsilon, thrice epsilon, 4 epsilon. Now, how can again I keep 3 particles into these levels so that my total energy is 6E? Earlier, many of you had already written them. So, I have missed who had written. So, let me just write the next. I could keep, I hope all of you will agree with me, if I keep 2 particles here and 1 particle here. Correct? Isn't it? 2, 1 plus 1, 2 plus 4 is 6. And all of you, please try to write. How will I write this? How will this information be written as the macrostate? First level has 2, second level has 0, third level has 0, and the fourth level has 1. So the next macrostate that we are now discussing is 2001. Right? 2001. Number of particles 3, total energy 6. Macrostate. Now, provided that this macrostate is there, Now we are ready to see how many microstates we can have. Remember, these two particles are occupying the same level. So even if I interchange their names, say when I write AB, AB in this case is exactly equal to BA. So I can have one microstate where A and B are here and C is here, which means I can write it as AB 00 C. Correct? Then I can also have, say, this 00A. This is another. And final, I could have 0A. I mean B. Correct? So either A or B or C, they are occupying the 4E energy level, and the rest of the two are in the first energy level. So corresponding to 2001, I can write three separate microstates like so. Correct? Very nice. So when I sum up for 2001, I will be able to have 6 microstates. Correct? And as you all have, many of you have already written, Rishabh has written, Arjun has written, that the last possibility of macrostate that we may possess is when all the three particles are in the second level. So 2 plus 2 plus 2 is 6. And how are we going to write this as the macro? We will write it as 0, 3, 0, 0. And since all the three are here, A, B, C, or when I'm interchanging the names also, will not have any difference. So how many number of microstates is available for 0300? How many microstates can we have? Only one, isn't it? And that will be written as 0, ABC 0, 0. So for the particular macrostate 0300, I have one microstate. So when I have to summarize my result for this given system, I have total number of macrostates 3 and total number of microstates 10. Right? Yes, Shomo, you're right that we will be writing it as 0 ABC 0, and all of you have written the correct answer that corresponding to this macrostate, there is only one microstate. So have you all understood how to do these problems? These two sums that we have done, this sum generally also comes in the exam. Okay, so now that you have understood this, it is time for us to summarize entire thing. So in statistical mechanics, what we will do? We will consider that the system is consisting of identical particles. And today, the system that we have considered, for today's lesson, we have also considered that they are distinguishable, which means I could distinguish from one particle to the other. I could name one person as A and the other particle as B. Fine. So we are going to have total number of particles in the system which is fixed to be N. The energy will also be fixed to be E. It will be in thermal equilibrium, and in this situation we will be writing its macrostate and microstate. Fine. So that is all in this case. And just I just remembered that one day Triti Nabo had asked, ma'am, what is thermodynamic probability? So just a small little, I'm not even going to talk about the formula. I'm just going to tell you in very short, what is this thermodynamic probability. Now, did you all notice that for 1110 macrostate, I had 6 number of microstates? So the number of microstates possible for one macrostate is defined as its thermodynamic probability. As simple as that. Please do not confuse with probability as such. When we talk about probability, it can only have a value within 0 to 1. Not that probability. We are defining something called the thermodynamic probability. And what is thermodynamic probability? Thermodynamic probability is the total number of microstates which is possible for a given macrostate. So for this, I have thermodynamic probability to be 6. For this macrostate, I have thermodynamic probability of 3. And for this, I have thermodynamic probability of 1. Alright. So that's all for today. I hope that all of you have understood the very simple mathematics that we have done. and this will help you in your exams as well, exam preparations as well. So that's all for today. Bye bye. See you all. Have a good day.